A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. You are welcome to the next edition of our online class for chemistry for Ss2 students at Islamic College Oshogbo. Today, inshallah, we are going to move to halogens. As you can recollect that for the past few weeks now, we have been talking about non-metals. So the set of non-metals we are going to talk about today are called halogens. Halogens are group 7 elements, the element that can be found in group 7 of the periodic table. They are so called because they are salt formers. When they react with metals, the product is usually salt, and the name halogen comes from two Greek words meaning salt former. Among the members of halogens that we have are fluorine, chlorine, bromine, iodine, and astatine. All of them are non-metals, and they have the electronic configuration ending with P5, meaning that they are in group 7. You know that group P block elements, their group are determined by adding 2 to the number of electrons in the last P subshell, and they are all diatomic, so they all exist as diatomic covalent molecules represented as X2, as you can see on your screen. In the periodic table, among all non-metals, there is no non-metal that is more reactive than halogens. They are the most reactive non-metals, and the order of reactivity is what you can see. Fluorine is the most reactive among them, followed by chlorine, followed by bromine, followed by iodine. This reactivity is because they require only one electron to complete the outermost shell, so it becomes very easy for them to attract the electron to themselves, and that means that they have high electronegativity. That is, when they are in molecules, they find it so easy to attract electron to themselves. Or you can also say that they have high electroaffinity, because when they exist in monovalent gaseous states, they attract electrons to themselves very easily. Now, if we say the halogens are the most reactive elements in the periodic table, and among halogens, fluorine is the most reactive, this means that fluorine is the most reactive non-metal in the periodic table. Because sometimes the examiner may want to test your knowledge and ask you to name the most reactive non-metal in the periodic table. The simple answer to that is fluorine, because it is the most reactive halogen. Any period that contains halogens will be the most reactive among them. Now, they have the highest electron affinity, just like I've said, and the electron affinity varies as the reactivity also varies. They have common properties that we can talk about for all of them. Among the common properties of halogens is the proportionation. When we say the proportionation, we mean the ability to react as oxidizing agents and reducing agents at the same time in the same equation. The most common example that will come to mind is the reaction of chlorine with water to form oxochlorate 1 acid and hydrogen chloride. Now, the same chlorine, if you consider the oxidation state of chlorine in chlorine molecule, it is 0. But in oxochlorate 1 acid, the oxidation number of chlorine is +1. So if you look at it that way, you say that chlorine has been oxidized, and if chlorine is oxidized, it means it's acting as a reducing agent. Now consider chlorine and hydrogen chloride. Oxidation number of chlorine in chlorine molecule is 0, but in hydrogen chloride, the oxidation number of chlorine is -1. If you look at it that way, chlorine has been reduced, meaning that chlorine is serving as oxidizing agent. So in this same equation, chlorine is reacting as a reducing agent and as an oxidizing agent. That type of situation is called the proportionation. So this is one of the reactions that halogens undergo. Also, all hydrides of halogens are acidic. Hydride of halogen occurs hydrogen halides. All hydrogen halides are acidic. Now, you may be required to compare one hydrogen halide to the other in terms of their acidity. Now, what makes an acid strong is ability to release hydrogen ion in solution. Now, fluorine is the most reactive because it is also the smallest among the halogens. Therefore, hydrogen fluoride will be a very strong, there will be a very strong bond between hydrogen fluoride, and that will explain why hydrogen fluoride is also exhibits hydrogen bonding. But that's not what we are even talking about here. Because of the smallness and size of fluorine, it is not as easy for you to release hydrogen ion in solution compared to chlorine, which is bigger in size than fluorine. And if you look at bromine is also bigger than chlorine. It means hydrogen bromide will furnish its hydrogen ion in solution more easily than hydrogen fluoride. And if you look at hydrogen iodide, it will furnish its ion in solution more easily than hydrogen fluoride. Therefore, hydrogen iodide will be the strongest acid among them because it finds it so easy to furnish hydrogen ion in solution. Hydrogen bromide will follow, hydrogen chloride will follow, and hydrogen fluoride will be the weakest among the acids. Even though fluorine is the most reactive, but the weakest acid among hydrogen halide is hydrogen fluoride. Please, I hope you understand that. Now, let's go to the next general property of halogens. Here you have hydrogen fluoride occurs as a fuming liquid, even though it is colorless, but it fumes. It fumes. Hydrogen fluoride in its own case is gaseous. Hydrogen bromide is a reddish brown gas. It's also gaseous. Hydrogen iodide is a violet gas. It's also gaseous. So among the hydrogen halides, it's only hydrogen fluoride that is colorless, and that is liquid. Both hydrogen fluoride and hydrogen chloride are colorless. Hydrogen bromide is reddish brown, while hydrogen iodide is violet in color and is also gaseous. So only hydrogen fluoride is occurs as a liquid among the hydrogen halides. Now, if you look at what we have been talking about so far, we have been talking about fluorine, chlorine, bromine, iodine, and we said that halogens are 5 in the periodic table. Astatine, we have not been talking about astatine because astatine does not occur in nature. It is rather an element, a halogen that is created as a result of radioactivity, and that is why it is not, its own property is not of importance to chemists. Now, physical properties of halogens. They don't have similar physical properties, and just like you can see that you have mentioned them now. In terms of their states, fluorine is gaseous, chlorine is gaseous, bromine is liquid, while iodine is solid. The physical properties change gradually as the size of the molecule increases. Now, the atomic size increases down the group, just like any group of elements that you want to talk about. That is from fluorine to iodine. Electron affinity decreases down the group. electronegativity decreases down the group. So it means as we go down the group, the reactivity will also decrease. As we go down the group, the elements change from gaseous state to liquid state to solid state. Now I've mentioned it that bromine is liquid, iodine is solid, but chlorine and fluorine are gaseous. Now there's one important thing that you need to note there as well. Mostly non-metals are in solid form. It is not so easy to find non-metal that is not solid, but bromine is in liquid form. So examiners are also take interest in this type of question. They will ask you, name one non-metal that occurs as liquid at room temperature. So the simple answer to that question is bromine. Bromine. If you look at the following table, you will see that the boiling points also vary as we move from the top of the table to the bottom. The boiling point increases. The boiling point increases from minus 220 degrees Celsius to minus 34 degrees Celsius to 58 degrees Celsius and to 184 degrees Celsius, which is that of iodine. Melting point also increases down the group from as you can see in the table, which I don't need to read to you now. Just look at the variation in the boiling point. It increases down the group as well. Now, this trend, what is responsible for the trend, especially in boiling point and melting point that you have just looked at? The melting point or the boiling point of a substance has to do with the type of force that holds the molecules together. And in all cases of the halogens that we are talking about, the molecules are held together by van der Waals force. And there's one property of van der Waals force that you have to understand. When the molecules are small, the van der Waals force is weak. The van der Waals force increases with the size of molecules. Remember, fluorine is the smallest among the halogens. So the van der Waals force holding fluorine molecules together will be weaker than that of chlorine. Chlorine is smaller than bromine, so the van der Waals force will also be smaller or be weaker compared to that of fluorine. That will compared to that of bromine, which is smaller than iodine. So the strength of the van der Waals force depends on size of a molecule. So somebody may ask you to explain. That is what the question can come in this manner, that arrange the following molecules in increasing order of boiling points, or arrange the following molecules in increasing order of melting points. Now explain your answer. So what you are going to, after arranging them based on the size of molecules, if it is increasing order of boiling point or melting point, you start from the smallest molecule to the biggest molecule. Then explain your answer. Your explanation will be that the strength of the van der Waals force increases with molecular size or molecular mass. Now, among the halogens, the one that is most commonly known and that is of most interest to chemists is chlorine, and that is why we are going to treat chlorine as a representative of halogens. Chlorine is one element that exhibits isotopy. There is chlorine 35 and chlorine 37 in nature, and the chlorine occurs in high abundance in seawater as well as in rock as rock salts, and in such situation it occurs in combined states, that is as sodium chloride. This is true for almost all the halogens, because halogens are very reactive. They are never found free in nature. So we cannot talk of chlorine existing free in nature. No, when we are talking about existence of chlorine, we will talk about it as in combined state, and we usually find it in seawater as well as in rocks and sodium chloride. Now, looking at the properties of chlorine, the color, we are just like we have said that chlorine is gaseous in state. So if you look at the color is yellowish green. In fact, that's from where the name is derived. So if you look at this video, the color of the gas that is issuing out from that test tube, look at it properly, it is yellowish green in color. Laboratory preparation of chlorine. Chlorine is prepared in laboratory by different methods, but the two main methods of preparing chlorine in the laboratory is by oxidation of hydrogen chloride acid. Oxidation of hydrogen chloride acid, otherwise called hydrochloric acid. The oxidizing agent may be manganese 4 oxide, it may be potassium tetraoxomanganate 7. Now, if manganese 4 oxide is used, then the reaction mixture has to be heated to achieve the desired results. But if it is potassium tetraoxomanganate 7, that is acidified potassium tetraoxomanganate 7 that is used, the reaction does now have to be heated. The reaction will just proceed without heating. Without heating. And in both cases, chlorine gas is evolved as a yellowish green gas. This is the diagram to show the laboratory preparation of chlorine. When concentrated hydrochloric acid is added to potassium tetraoxomanganate 7 acidified in a flask, you know hydrogen chloride gas is a fuming liquid and is highly volatile. So it would come out together with the chlorine that is formed. That is the unreacted hydrogen chloride gas will come out with the chlorine gas that is produced. And that is why this flask is necessary. So this flask that contains water is there in order to absorb the unreacted hydrogen chloride acid that will come out in gaseous form with the chlorine. Then the next flask that we have there is containing concentrated tetraoxomanganate acid. So the purpose of that acid is to serve as drying agent, to dry the chlorine gas, and the chlorine gas is collected by downward delivery. And this method of collection should tell you something, telling you that the gas is denser than air. Any gas that is collected by downward delivery, otherwise called upward displacement of air, is denser than air. And if you actually determine the molecular mass of chlorine, you would discover that it is 71, far higher than that of air. So, and that's 72. It's 71, yes, 71. So far higher than that of air, showing that it is much denser than air. Industrial preparation of the gas. Chlorine is prepared industrially by electrolysis of either brine or molten sodium chloride. If you are using molten sodium chloride, what you just do is that after melting it, we pour the molten sodium chloride in the electrolytic cell. Sodium ion will go to their cathode, chloride ion will go to their anode. And at the end of the electrolysis, sodium metal will be deposited at the cathode, chlorine gas will be liberated at the anode, and that is all. If you are using brine, you have sodium chloride solution concentrated. So at the cathode, the normal reaction will take place. Hydrogen gas will be liberated, as we have known. But at the anode, chlorine, being more concentrated than the hydroxide ion, will be discharged in preference of hydroxide ion, and at the end of the day, chlorine gas will be liberated at the anode. So either way, whether we use brine or molten sodium chloride, we are going to get chlorine at the anode. Now, physical properties of chlorine. The physical properties of chlorine include its color. It is a greenish yellow gas at room temperature. It is denser than air, just like we have said, and therefore it is collected by downward delivery or upward displacement of air. It is a poisonous gas, therefore it should be prepared in a fume cupboard. That is the safety precaution that we need to put into consideration. For any gas that we say is poisonous, or any gas that is poisonous, should be prepared in a fume cupboard. It can easily be liquefied under pressure, and it is moderately soluble in water. It is not highly soluble, it is not totally insoluble. It is moderately soluble. Then it turns damp blue litmus paper red and then bleaches it. So it will not only turn blue litmus paper red, but it also bleaches as it turns it red. We are going to look at that bleaching action as we progress in the lesson. The chemical properties. When it reacts with water, it forms two types of acid. Also chlorate 1 acid and hydrogen chloride acid, as we have mentioned when we are talking about the proportionation. So it forms HCl and HClO. This can also be written as HOCl. So then, although it does not support combustion, but we allow some substances to burn in it, mostly metals and non-metals. In the presence of sunlight, it reacts explosively with hydrogen. And to form hydrogen chloride gas. Now, anyway, as we progress, we would understand the difference between hydrogen chloride gas and hydrogen chloride acid. Hydrogen chloride acid is also called hydrochloric acid. So, because the two should not be used interchangeably. When we have hydrocarbons and chlorine, hydrocarbons burn in chlorine to deposit carbon and produce hydrogen chloride as well. And this reaction is usually demonstrated using turpentine. Turpentine is C10H16. So when it comes in contact with chlorine, it forms carbon as well as hydrogen chloride gas. The equation you can see displayed on your screen shows how metals burn in chlorine. Aluminium with chlorine to form aluminum chloride, copper with chlorine to form copper 2 chloride, iron with chlorine to form iron 3 chloride, phosphorus with chlorine to either form phosphorus 3 chloride or phosphorus 5 chloride. If chlorine is in excess, it will form phosphorus 5 chloride. But if chlorine is in limited supply, it will form phosphorus 3 chloride, as you can see in the equations displayed. Now, chlorine is also an oxidizing agent. Ordinarily, chlorine is an oxidizing agent, but when it comes in contact with water, it disproportionates, that is, acting as both oxidizing agent and reducing agent at the same time. But in ordinary form, chlorine is an oxidizing agent. And to demonstrate its oxidation ability, you have some of the reactions here. When it reacts with ammonia, it forms nitrogen and hydrogen chloride gas. But if the ammonia is in excess, the hydrogen chloride gas formed will react with more ammonia to form ammonium chloride as dense white fume that we have talked about when we are talking about ammonia. We are still going to look at it again on the hydrogen chloride, which is going to be the next lesson, inshallah. When hydrogen sulfide bonds in chlorine, we have hydrogen chloride and sulfur being formed. This also shows that sulfur is oxidized from -2 to 0, and that shows that chlorine is acting as an oxidizing agent. Also, when chlorine reacts with iron 2 chloride, which is always green in solution, iron 3 chloride, which is brown or reddish brown, or sometimes yellow, is formed. So this also shows that it's an oxidizing agent, and this property is also true of all oxidizing agents. They all oxidize ion 2 ions in solution to ion 3, and that therefore changing the color from green to brown or reddish brown or yellow. It dissolves in water to form two types of acid, as we have said before. Displacement reaction. Chlorine displaces other halogens that are lower than it from solution. We have arranged them in order of reactivity before. Chlorine is more reactive than bromine, is more reactive than iodine. So if we have a compound of bromine coming in contact with chlorine, that bromine will be liberated from that compound. So chlorine will take its position. Also, if you have a compound of iodine reacting with chlorine, chlorine will take its position in that compound while iodine will be liberated. This explains why starch iodide paper, when placed in a gas jar containing chlorine, turns blue-black. Because when chlorine reacts with potassium iodide, which makes the iodide paper to be iodide, it forms potassium chloride and iodine. The iodine, we all know that when it comes in contact with starch, will turn starch to blue-black. So if a starch iodide paper is dipped inside the gas jar containing chlorine, it turns to blue-black coloration immediately, and that is used as a test for chlorine in the laboratory. Reaction with alkalis. Whenever chlorine comes in contact with cold dilute alkali, it will form the oxochlorate 1 salt of the alkali metal and chloride salt of the same alkali. Look at the example given here. Chlorine reacting with sodium hydroxide will form sodium chloride, sodium oxochlorate 1. This can be written as NaOCl or NaClO and water. So this can be looked at as a neutralization reaction, because we have an acid reacting with an alkali to form two salts and water only. Now, this is the reaction that is used in making most of our domestic bleach. When chlorine gas is just bubbled into any alkali, sodium hydroxide, in our laboratory, for example, we are going to obtain this solution. This reaction mixture is the content of most of our domestic bleach, like jik or hypo, or most of those other domestic bleach that we use, that is those ones that are in liquid form. But if it is hot concentrated alkali that is used, instead of forming oxochlorate 1 acid that we have here, it will form trioxochlorate 5 acid. That's just the difference. It will form the chloride salts, trioxochlorate 5 acid, salts and water. So it will form two salts and water. It will form the chloride salts, trioxochlorate 5 salts, as well as water. If chlorine is passed into dry slaked lime, that is calcium hydroxide in solid form, it will form bleaching powder. The formula of bleaching powder is calcium CaOCl2.H2O. That is calcium oxochloride monohydrate. And that is what we call that is what we use as bleaching powder. Chlorine water. That's the next thing that we need to talk about. We have mentioned it before that when chlorine dissolves in water, it forms two types of acids. Also chlorate 1 acid and hydrogen chloride acid or hydrochloric acid, as well as water. So this mixture of the product is what we call chlorine water. And when chlorine water is exposed to the atmosphere, oxygen is usually liberated, as you can see in the equation. Now, this is also of interest to most examiners. Sometimes they will just give you a diagram showing and they are labeling the solution in the diagram as chlorine water. They will now ask you a question that the gas that is liberated is what? Most students will rush to choose chlorine, because you can see that it is chlorine water. So when it is exposed to sunlight, what gas do you expect that it will liberate? But the gas that will be liberated is actually oxygen, because what will happen is that the chlorine water, which contains mainly HClO, will produce HCl plus O2. So the gas liberated is oxygen. Please take note of that. Don't be deceived. Bleaching action of chlorine. The bleaching action of chlorine is because of its ability to deproportionate in water. So when it dissolves in water, it forms the two types of acid that we have mentioned. And because oxychlorates one acid, when it comes in contact with dye, it will liberate its oxygen atom. When oxygen atoms react with dye, which is colored, it will form dye plus oxygen, which is colorless. Now, if you compare this bleaching action to the one that we have learned in the past, that of sulfur 4 oxide, you will discover that sulfur oxide will take up oxygen atom from a dye, and the dye will become colorless. But in this case, the bleaching agent adds oxygen to the dye, and the dye becomes colorless. So there are two different forms. It means sulfur oxide, why it bleaches as a reducing agent. Chlorine bleaches as an oxidizing agent. Even though both of them bleach in the presence of water, both of them require water for their bleaching action. So that is the main difference between bleaching action of chlorine and sulfur oxide, is that sulfur oxide bleaches as a reducing agent, chlorine bleaches as an oxidizing agent. And because of that, the bleaching action of chlorine lasts long, because it has added oxygen atom to the dye. To remove that oxygen atom is not as easy compared to sulfur oxide that will take away oxygen atom from dye, which can easily recapture the oxygen atom from the atmosphere. So bleaching action of chlorine is relatively permanent compared to that of sulfur oxide. Uses of chlorine. If I ask you to list the uses of chlorine by now, you should be able to mention some things. And the most common one, or the easiest one that will come to your mind, is the one that you have just mentioned now. Chlorine bleaches substances. So chlorine is a bleaching agent. That's one of its uses. It is used as a bleaching agent. It's also used as a disinfectant or as a germicide. And this will also take us to its use in the treatment of water that we have talked about in the past. So it is used in treating water that is meant for town supply. It's also used in chlorination of organic compounds. Just like we have mentioned, it reacts with turpentine to form carbon and hydrogen chloride. Sometimes when it comes in contact with other hydrocarbons, it will form chloroalkane. Chloroalkanes also, there are different forms of chloroalkanes that also have their own different uses, which we are going to be talking about when we get to organic chemistry. I pray Allah grants you understanding. Assalamu alaikum wa rahmatullahi wa barakatuh. Meet you next class.